Hey guys, it's Ron. So I've done a previous video on subnetting, and in that video I talked about converting between binary and decimal. Well, it's an important skill to have in the networking community, but another base system is the hexadecimal system, and you kind of need to know how to use that as well, because it's going to allow you to look at a hexadecimal number that you're inputting into like the configuration register and know which actual bits you're setting. All right, and without being able to convert between binary, decimal, and hexadecimal, that's going to be kind of difficult. So here we go. So binary is the base 2 system. I have the 0 and the 1 digit. Decimal is the base 10 system. I have 0 through 9 digits. And hexadecimal is the base 16 system, and I have 0 through 9 and A through F, or alpha through foxtrot. Okay, so I'm gonna use all of those digits to represent basically the same number, just in different base formats. One thing to note is that in order to go from decimal to hexadecimal, you often have to go through binary and vice versa. So let's get into it. Binary to decimal. Previously explained this in my other lab, but it's much the same stuff. If I want to represent a number, the position that number is in, carries some weight. So like in the decimal world, I have 10 digits that I can work with. So if I do 10 to the 0 power, I'm in the 1s column. If I'm 10 to the 1 power, I'm in the 10s column. If I'm 10 to the 2 power, that's 10 times 10, which is 100, so I'm in the hundreds column, and vice versa. This is the thousands and on up the line. So you're already doing this with the base 10 system. You're just now adapting it to the base 2 system because we only have 2 digits. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and all the way up the line. Okay, so these are decimal equivalents of these positions for the binary numbers. All right, so if I want to convert, let's say from decimal 10 up to a binary number, I'm just going to say, hey, can 128 go into 10? No. If it can't, it's a 0. Can 64 go into 10? No. Neither can 32 and neither can 16. But 8 can go into 10, so I put a 1 there. 4, let's see, 8 or 10 minus 8 leaves me 2. So can 4 go into 2? No. Can 2 go into 2? Absolutely. And then I'm left with 0. All right. So 150. Can 128 go into 150? Yes. Yes, it can. So bring up my calculator. 150 minus 128 leaves me 22. Can that 64 go in? No. 32? No. 16 can. So I'm going to subtract 16, and I'm left with 6. So 8 can't go into 6, but 4 can. Oops. And it leaves me with 2. 6 minus 4 is 2. So that's there, and I'm left with 0. 220. So 220 minus 128 leaves me 92. So I know I've got a 1 here, and I've got a 1 there. I'm going to subtract the 64, left with 28. So I can't do that, but I can put 16 into it. Minus 16, I'm left with 12. Now I know 8 plus 4 is 12, so 1, 1, and then 0, 0. All right. So these are the binary equivalents of these decimal numbers, and I can go backwards too. If I'm given the binary number, I can generate the decimal number just by adding up the placeholders that are 1s. Alright, so I'm going to add up 4, I'm going to add up 8, I'm going to add up 16, I'm not going to add up this digit, I'm going to add up 64, and I'm going to add up 128. So anywhere where there's a 1, I'm going to add that number in. So let's see, 128 plus 64 plus 16 plus 8 plus 4, and I get 220. So you can easily convert from a decimal number to hexadecimal, or from decimal to binary, by making sure, can this go into that digit, can this go into that digit, and working your way down the line. And then on the opposite side, anywhere where there's a 1, you add in that place, and you'll get the decimal equivalent. Alright, so let's talk about hexadecimal. In hexadecimal, remember I have 0 through 9, and those equate to 0 through 9 in decimal. But I also have A, B, C, D, E, F, and that represents 10, 11, 12, 13, 14, 15. So I have 0 through 15 that I can represent with 0 through 9 and A through F. Alright, so 16 total numbers. Alright, now when going from binary to hexadecimal, I've got a number here. Each hexadecimal digit represents one nibble. Alright, because with 4 digits you can represent 16 total numbers. Alright, so we're going to break these into their nibbles. So 1, 0, 1, 1, and then the last 4, 0, 0, 1, 1. And then we're going to take this number and we're going to convert it, alright, using this chart. Alright, so let's see. 1, 0, 1, 1. This is a 0 column, 1 column, 2 column, 3 column. So this is 8 plus 2 plus 1. Alright, so we end up with 13 in decimal. But a 13 here equals a D.